Hello, everyone, and welcome to today's webinar, Engineering Extended Range Hybrid Systems. I'm your moderator, Amanda Hosey, and joining me for this 60-minute program are Jason Glass and Matrishvan Raval of Turntide Technologies. Jason serves as the head of product for electric drive units and diesel hybrid systems at Turntide, where he leads go-to-market development for EDUs and series diesel hybrid platforms, while advancing original IP. He's an Air Force veteran, a motorsports competitor, and a hands-on engineer turned electrification strategist who bridges deep industrial drivetrain roots with cutting-edge axial flux motor commercialization across defense, marine, off-highway, and classic vehicle markets. Matrishvan is Turntide's head of product for high-performance motors. He has extensive experience developing and commercializing electrification and control systems products across automotive, motorsports, and aerospace sectors, and previously led engineering teams at McLaren Applied for automotive and motorsport control systems. Matrishvan is an alumnus of the General Management program of Harvard Business School and holds a bachelor's degree in engineering and communications and electronics and a master's degree in safety critical embedded systems from the University of Leicester. If you have questions for today's speaker, please send them using the Q&A box and we'll address as many as we can at the end of the program. Also note that a PDF as well as other resources a PDF of today's slides as well as other resources may be found within the resources box on your screen. Now on to the presentation. Welcome Jason and Matrishvan.
Hi, everyone. Good to be on the presentation. So today we'll be looking at how we can engineer extended range hybrid systems and a multitude of other systems using high performance axial flux motors. So I'll go through what the underlying technology behind the axial flux motors is and what advantages it provides and how those advantages translate into actual applications. The axial flux motor is very versatile and adaptable across a whole range of industries. Given its compact size and high performance at high torque, low speed operating regions, it's adaptable in a number of industries, including commercial vehicles, off-highway vehicles, construction, marine, and other applications. Let's take a look at what makes up an axial flux motor, the topology that we at Turntide have adopted, and how that is versatile and adaptable across a range of industries. My colleague Jason will then go through its application in extended range hybrid systems, and I'll finally take over and look at the electric PTO systems as well. So an axial flux motor has the magnetic flux that is parallel to the axis of rotation. That is the key difference that makes a difference from radial flux motors, where the Emac flux is radiating outwards from the axis of rotation. Now, this geometrical difference is the core reason for all the advantages that you see in terms of performance and compactness. In terms of the construction of the axial flux motor, we have adopted a dual stator single rotor topology. So there's two stators on either side, and the central rotor is composed of reinforced polymer spider cage, and there are magnetic slots in which high performance neodymium magnets are placed, and that is banded with a carbon fiber tape. The banding and balancing of the rotor ensures its operation in unbalanced high NVH scenarios as well. The stator cores on either side made of electrical steel laminations with copper wire windings, and there's cooling jackets on either side as well for thermodynamic cooling of the stator windings. This is coupled with a top box for high voltage electrical connections and inverter connections on the top. So this is what makes up the geometry of an axial flux motor. This geometry also allows for a torque density that is typically twice to 4 times of a radial flux motor. The reason for that is the high density of the magnetic flux that's concentrated across a short axial length. What that does is it provides some inherent advantages that make it suitable for hybrid systems. The axial length of an axial flux motor is very compact. We typically get applications of up to 200 kilowatt peak in an axial length that is as short as 200 250 millimeters, and up to 100 kilowatt continuous for an axial length that is as short as 125 millimeters. So this makes it very suitable for slotting into applications where you have to do a retrofit. In most internal combustion engines, um, and most ICE-driven applications, internal combustion engine-driven applications, you don't have enough space to retrofit it with a radial flux motor because the length of the radial flux motor usually does not fit into the space claim that's available. So that compact horizontal design of the axial flux motor allows you to integrate this easily into hybrid systems. The the torque and power to weight ratio is also very superior. It's usually 2 to 4 times of equivalent radial flux motors. The lower inertia of the rotational mass also ends up giving you advantage in terms of longer life. So these tend to have very high MTBF figures, typically 30 to 50,000 hours. So that is a high reliability figure as well. And the electromagnetic design that's going into the motor allows for an IE4 or higher class of efficiency. So typically it's about 96% in terms of its efficiency. The design of the axial flux motor has been done such that it is scalable across a wide range of power solutions. There's two axes on which the scaling can be done. First is the diameter itself. The torque output of the axial flux motor would vary with the cube of the diameter, whereas in a radial flux motor, the torque output varies with the square of the diameter of the motor. So as you diverge in diametric scales, the axial flux motor tends to have an outsized advantage. The other scalability feature is the stacking. So these are stackable in multiple stacks, up to 2, 3, and 4 stacks of the motor. So in depending on the form factor in which you want to have the space claim limited to, and depending on the torque and speed profile that you require, you can scale it in either direction. You can either scale it from a diametric point of view to get a higher torque, lower speed, torque speed profile, or you can scale it in a radial form across the axis by multiple stacking, where you can just increase the multiple of the torque and the power output. These are also available to be fitted onto multiple SAE flanges and has a female bore motor design that makes it very versatile and universally applicable for most applications. And we can also integrate it with any transmission or transfer cases for EDU type applications. So yeah, as I said before, the motor is very suited for hybrid systems because of its form factor and ease of integration. There are four readily available products that are suited for hybrid systems. So product ranges of 400 and 430 millimeter outer diameter in both single and double stack configurations will give you power range from around 100 to 200 kilowatts. Um, and those are readily available off the shelf. And they have been proven in actual customer applications, some of which we will go through later to provide TCO improvements. One of the key TCO improvement feature is possible because the motors are speed matched with the engines. So the axial flux motor characteristics in terms of the torque speed profile inversely vary with the diameter of the axial flux motor. So the largest diameter motor, i.e., the 430 millimeter diameter motor, is speed matched with a diesel engine. So if you look at a torque speed curve, the base speed of the motor will typically match with the optimum fuel burn point of the ICE engine, and the maximum speed of the motor will typically match with the overspeed condition of the internal combustion engine. So that speed matching is what is allowing us to do a proper power blending between the internal combustion engine and the electric motor. And the algorithm that sits behind the power blending can also provide outsized advantages in terms of the final range. So this is a key feature that enables the axial flux motors that we have designed at Turntide to provide an outsized TCO advantage. Along with the TCO advantage, you can also reduce the planned maintenance and downtime of your overall vehicle. The reduction in the mechanical components also allows you to have reduced maintenance cycles, reduced oil changes, and there's very little degradation. The engine downsizing that can happen along with a hybrid system also allows for a lower fuel burn. So all of these things contribute towards a lower total cost of ownership. Usually, we see that customers who have integrated the axial flux motors are able to get a payback period on the initial investment or the premium of electrification within a 2 to 3 year period. And given the life of 10 to 15 years or higher of the overall system, the rest of the years are just an improvement in terms of the overall TCO. So a 2 to 3 year payback period and a long uh, period of reaping the benefits of having an electrified system. To look at more of the practical examples of how we've done this in a hybrid system, I'll now pass it on to my colleague, Jason Glass. He'll take us through actual hybrid systems in which these have been implemented. So, Jason, over to you.
Thank you, Matrishvan. Appreciate that. Yeah, so I kind of manage a lot of our practical application side and a lot of the prototyping that we're doing here at Turntide. And one of the most exciting things that we've been working on recently is the series hybrid design and range extended design. And one of the things that Matrishvan brought up, and that's really key to hybridization or range extension, is the versatility of the Turntide motor, where we can go from 55 kilowatts to all the way up to 1 megawatt of power production, peak power production on a platform. And the nice thing about the design, and one of the pictures you see there, is how we're able to drop directly into an existing platform. And currently, one of the areas where we're doing that is last mile delivery trucks, where you can take a large box truck, class 6, 7, and 8, where you can remove the transmission, add in the power generation unit directly onto the back of the diesel engine, and then directly drive the transfer case or rear axle off of a gearbox, utilizing an actual flux motor. So it's a really exciting time for us, and we'll kind of walk through some of those examples and look at some of the different options that you guys have when it comes to series hybrid or range extension, all the way down to compact ICE designs and the application of those. So, but the really exciting part of this is it doesn't require a redesign of a current chassis. So you can take an existing fleet or an existing chassis design today, lengthen the drivetrain by 125 millimeters, and add in a hybridization drive or a power generation drive. So it's really exciting time for us as a company. Excuse me. And the power economics here that go into the advantages that you have is the integration with the system. And one of the things that we look at is efficiency and adding more power. So whether it's a low end torque requirement for last mile delivery, or if it's range extension, you get both of those with the axial flux motor design in the compactness. An example of that, and you'll see later in the slides, is the ability to fit the entire drivetrain within the same space claim as a traditional transmission. So it's very exciting to kind of walk you guys through that. Excuse me. One of the things that we've really focused on and being able to solve for you guys is the complexity of integration. And our motors are designed and sized such that they match the SAE bell housing on the back of a motor. So if you're dealing with, say, an SAE 5, SAE 4, you may want to use a 300 millimeter motor or a 400 millimeter motor, where when you get into the SAE 3, SAE 0, or SAE 1, you're going to want to use that 430 millimeter motor. And like Matrishvan said, they're kind of speed matched. So if you're using a large 6.7 liter diesel engine or 6-liter diesel engine, that motor is going to perform its best BSFC at about 1800 RPM, somewhere in that range. Some are as low as 17, some are as high as 1850. But that is the ideal position for that motor to be running. And because of its compact size, it fits right into the drivetrain. And with range extension, as you guys all know, you've got an ICE motor that's running a generator. You have electric drive that's running your traction drive side. But with the stackable nature of our motors, we also alleviate a drivetrain failure point, where if you have one motor that goes down, you can still power the system with one of the other motors. So it adds in a safety factor, which is big for marine and some commercial vehicle applications. And then where you have space constraint, the size of the motor works really, really well with smaller form factor vehicles. So say a front wheel drive, last mile delivery van, or or your existing chassis designs. The other advantage that we have too, and this is where it really gets exciting, is our weight mitigation side. So if you have a current chassis today and you're running a 6.7 liter or 6-liter diesel, 4.5 liter diesel, you can actually take that larger diesel engine, which, as you guys know, they weigh a lot. You can actually downsize from, say, a 6.7 liter diesel to a 4.5 or even a 2.8 liter diesel engine size, generate the power that you need to keep your battery at ideal SOC, and save the weight because you're going to be adding a battery. So where the Axial Flux plays into that is our weight to power ratio is much, much lower than it would be with a radial. So we can generate more torque with a lighter footprint, allowing you to use a battery that's optimized for your chassis design. Excuse me. So as we start to look at how we're working these two systems together, it's really exciting because the algorithm side of it and the software and integration side of it is starting to change, in that we can see higher performance from a series hybrid or a range extended vehicle than we have in the past. And that's because of the weight reduction. The other side of this that we're seeing is performance gains from the low torque side, but also in noise reduction in inner city areas or areas of population where they don't want diesel idling or engine idling. The series hybrid or range extended hybrid for last mile delivery is starting to take and see a lot of momentum, because when you're in those urban areas, you're able to turn off the ICE engine, run specifically on battery, so that in that urban area, you don't have your tailpipe emissions, you don't have the noise of an idling diesel, and you're able to run just on that battery and then have the diesel or the ICE engine come back on board and bring you back to ideal SOC when you're leaving that area. Excuse me. Sorry, I've got a little bit of a cold. The other part of that Matrishvan brought up too is reduction in TCO. And one of the areas that we talk a lot about is getting that ICE into its optimal BSFC position to have the right operating temperature, the right turbo or air intake temperature, maximize fuel efficiency, and optimize torque. So much in an last mile delivery truck, or one of the interesting areas where we're testing it right now is in garbage trucks, because they're so heavy, large hydraulic systems, but it's constant stop and start. So where electrification of the powertrain adds that low end torque to get the truck moving, it also reduces the amount of noise because the diesel is constantly revving up to move the truck forward. And the heavier they get, the more emissions they have and the more noise they make and the more fuel they consume, where keeping that diesel in a very specific running condition means we can soften the exhaust, we can produce the amount of power that we need and reduce the noise emissions and the exhaust emissions from that system, while also decreasing heavy braking, which is going to wear your brakes out sooner. It's harder on the transmission because you're kind of running between first and second gears continuously. So you're not getting optimal transmission usage. So going to a series hybrid or range extended version in that specific application, we've seen huge increases in performance and massive decreases in TCO. Again, we're keeping that diesel in that optimal, or the ICE engine in that optimal position. And it also goes all the way down into your smaller diesel engines. So your 1.8, 2.8 liter and smaller systems, where normally you would have to have a system that ran at a very high rate of speed or high RPM, which generates a lot of noise in the exhaust side of it, and also creates a lot of exhaust noise and then the potential there. So we're seeing a lot of decreased footprint, allowing us to decrease the size of that motor, which is really exciting. Practical applications. One of the systems that we're developing today is a small 2.8 liter or 4.5 liter series hybrid generator. It's based off of the Cummins. You can use any diesel you want. It's not specific to Cummins. But we're building today a practical application and tester model to demonstrate this footprint, where with that 2.8 liter, we're able to generate a continuous 70 kilowatts of power. That power is then fed into a 55 kilowatt hour battery. And we're seeing about a 30% increase in fuel efficiency for last mile delivery. It's a very compact package, as you can see with the picture up in the corner there with the diesel. That bell housing adapter and the motor itself only grew by 130 millimeters. We removed the transmission. This particular one, you can see the stub shaft sticking out the back side. The customer wanted the potential to be able to run a pump off the back of the generator as well. That's why you see a stub shaft there. But we're able to really decrease the size, where typically this particular platform would have used a 6.7 liter diesel with a power takeoff to run a hydraulic pump. Now we've downsized to a 2.8 liter diesel, and we're still able to run that PTO pump for hydraulics. So very, very compact package, but it's very, very torque dense. So we're able to generate a great deal of power off of that design. The other design that we're looking at right now and developing internally for production is kind of a flexible hybrid drive, where we're utilizing 2 axial flux motors and a clutch system, where you may have a critical system or a critical application, a defense application, or maybe an emergency vehicle, where if you have a failure in the drivetrain, you want to be able to switch over to a true ICE drivetrain. So you're able to switch from a series hybrid drivetrain or range extended drivetrain into an actual ICE drivetrain. So we're actually developing a clutched version or a dual clutch version that allows us to switch between multiple modes. So we can go from a ICE drivetrain to a series hybrid drivetrain to a parallel drivetrain to a BEV drivetrain, all within the same unit. So it's a very exciting time where this particular drivetrain can produce, with 150 horsepower, we're generating 410 horsepower peak with the electric drive. So we're able to kind of manage a lot of really interesting systems and develop that further. And another use case for this is, again, that series hybrid or extended range. And I'll pass that over to Matrishvan to kind of talk a little bit more about that.
Thank you, Jason. So yeah, as Jason mentioned, there are a number of practical applications where we've seen the axial flux motor be integrated into series and parallel hybrid systems or multiplex hybrid systems. One of the most important applications that we have seen this integrated in is commercial vehicle electrification. So what I have here is real world examples of various gross vehicle weights. They're typically trucks or other commercial vehicles. What the continuous electric power requirements in those electric vehicles were, and what axial flux motor we have used. So this goes to show that there is versatility in terms of the GVW rating and which of our axial flux motor range fits with them. So a 12-ton GVW truck application required around 73 kilowatts of continuous power, for which we had the AF300S, which is a 300 millimeter outer diameter single stack motor. A slightly larger version was the 19-ton, where we applied the AF400S motor. And then double stack versions of the 400 motor for the 33 and 55-ton applications. In this case, we were actually able to downsize the engines that gave the OEM a TCO advantage, a measurable TCO advantage. And we were also able to design, given the female bore nature of the axial flux motor mechanical interface, we were also able to design a two-piece custom shaft that allowed integration with the engine on one side and the transmission gearbox on the other side. So this has been a really successful example. There are many similar examples of commercial vehicle electrifications where we've not just provided the electric motor, but also the associated inverter. The advantage that we get by providing the inverter as well, which we have in-house capability for, is we can fine-tune and match the highest efficiency operations of the motor. We undergo detailed inductance map creation activities, both from a simulation standpoint as well as a dyno testing standpoint, and pair our inverters and motors together. So we were also able to provide the matched inverter both for 400 volt systems and 800 volt systems for our customers. One of the other applications that I want to take a look at is power takeoff. Now, if you imagine any work truck, be it a crane or a hoist, or even cement mixers or garbage collectors or refuse collectors, they usually have a system which takes power from the mechanical engine through a mechanical gearbox arrangement. Now, when the whole system is electrified, either in a hybrid fashion or in a pure BEV fashion, what you end up requiring is an electric PTO, an electric power takeoff system, which is essentially taking power from the battery and delivering it in a mechanical work fashion through the inverter and ultimately the motor. Now, there are a few advantages that an electric PTO gives you over a mechanical PTO. With an electric PTO, you can have an operation that does not require engine idling. So going back to some of the points that Jason mentioned, there are areas which require noise-free operation. There are city guidelines and city laws in construction areas that require noise-free operation. So that is something that an electric PTO enables you to do. The inherently noise-free nature of the electric motor and the electric powertrain allows you to have a non-engine idling operation and still deliver the electric power and the mechanical power that's required. If it is a hydraulically driven and hydraulically actuated system, you can much easily and much clearly control the variable speed and flow required from the hydraulic system. The control fidelity and the control responsiveness that an electric system provides is much higher than what a hydraulic or mechanical system can provide. Usually, the efficiencies of hydraulic systems range between 40 to 60%. The ePTO would be easily 90% or above in terms of overall system efficiency. So that these are some of the inherent advantages that you can get by moving to an electric PTO. So you basically, in terms of what it means in terms of real life examples, you get full torque at 0 RPM. So if you want a high torque, low speed operation without requiring an engine driven PTO, an electric PTO enables that for you. You're essentially decoupling the performance of your mechanical system or your work truck system from the characteristics of the engine at a high efficiency, which again gives you outsized advantages in terms of TCO and in an environment where you can do quiet, idle free or engine idling free work as well. Where the Where the Turntide EPTO comes in is the control fidelity and the compactness of the system. So we have designed inverters and motor pairing, which gives us the fastest control response times, um, fastest response times in terms of managing variable speed and variable flow of hydraulic systems as well. We can handle high peak loads. The typical ratio of peak torque to continuous torque in terms of axial flux motors is usually 2.5 times. With most conventional radial flux motors, that ratio would be around 1.5 to 2. So if you, as many of these work truck applications do, you end up requiring high peak stationary operations. And that's exactly what a turntide axial flux powered EPTO provides you. And as far as flexibility of mechanical interfaces go, these are available in various forms, be it standard splines from an ISO specification or various DIN flange options as well. So given the female bore nature of the electric motor, we are able to design in a number of flexible mechanical interfaces that gives the OEM the flexibility in terms of mechanical interfaces for the end application as well. So whether it's a construction equipment or an earth moving equipment, whether it's an application for a compressor use case, various municipal trucks or hydraulics in off-highway equipment or marine equipment, the EPTO tends to work really well. We'll be launching some of these products in the upcoming IAA trade shows as well. So you're welcome to come and take a look at that. So yeah, that's one of the key advantages of going from there's two layers of advantages here. One, going from a mechanical PTO to an electric PTO, and then from going from a generic electric PTO to a turntide axial flux driven electric PTO. We have systems that we've deployed in the 50 to 150 kilowatt range of continuous power, and that's a production ready solution that's deployed in field today. So hopefully you've enjoyed our explanation of the axial flux motors, its various real-world applications in hybrid and pure electric systems, and how EPTOs would be a good advantage over mechanical PTOs as well. I think at this point we're happy to take questions, so I'll hand over to the moderators for fielding any questions our way.
All right. Thank you so much, Matrishvan and Jason, for the great presentation. Just a reminder to those of you in the audience, you can still submit questions for the speakers using the Q&A box on your screen. But we have several that are already in, so we can go ahead and get started. Let's see. First up, Glenn asks, any gas engine vehicles using the axial flux motors?
Yeah, I can take that one. Go ahead, Matrishvan, go ahead.
No, so in terms of versatility of the motors, the speed range of the motor and the versatility of it ranges from a maximum speed of about 12,000 RPM all the way down to a maximum speed of 3,700 RPM. So what that range provides is suitability with low speed diesel, low speed petrol, high speed petrol, and any other ICE engine combinations that you can think of. So depending on the particular ICE engine that you want to couple the system with, we can select the right diameter class of the motor with its torque speed range and provide the right stacking as well. So in terms of applicability, it's applicable across fuel types, and we are basically fuel agnostic.
Okay, wonderful. Thanks so much. Let's see. Are there speed limitations?
Yeah, Jason, you want to take that or?
Yeah, so I think the speed limitations based on the diameter of the motor. So the smaller the motor that we use, the higher the RPM the motor can handle. So typically, if we're looking at a smaller petrol engine that's going to run at a higher RPM, we'll use a smaller diameter motor. So let's say you're running a 1.8 liter, just randomly pick a name, a Honda motor. That's going to run at a higher RPM, we would use a 300S or a 250 millimeter motor in order to speed match with that motor to get the best performance that we can. Where when we get into diesels, the SAE3, your 4.5 liter, 6.7 liter, they're only going to be able to run at 3,700 RPM max speed. So we use a larger diameter motor to produce more power. So it kind of depends on the platform that you're using. But our highest speed motor is about 12,000 RPM in the 250 millimeter range.
Okay. All right. Sorry about that. Okay. So kind of a multi-part one here. Let's see. Mark asks, what happens in an edge case duty cycle where battery is depleted on a long loaded uphill with a reduced displacement? Is the axial flux able to run at reduced RPM to still make the grade at a speed that matches the power of the smaller motor, similar to downshifting if a large engine derates to lower power?
Yeah, so I'll take that one. So if you're looking at the prime example of that is one of the customers we're working with is looking at heavy loads in the mountains. And what we're developing for them, and this is kind of still in the development stage software wise, is the ability to route map and calculate SOC for a specific grade and climb. So that we ensure that the battery is at maximum SOC before they start their climb. And then as they climb, we bring the motor to peak power to ensure that we're keeping the battery above minimum SOC and then generate enough power. And then we do have what would be a kind of a rescue mode or a crawl home mode, which would allow for the diesel to produce the same amount of power it requires to climb a grade. So you're going directly from diesel power to electric power generation directly into the motor to maintain hill climb and speed control. And for safety reasons, also be able to hold the vehicle still if they had a brake failure or something like that.
All right. Thank you so much for all that information, Jason. Let's see. Next up, Daryl says, maybe I missed this in the presentation, but how are parking brakes incorporated on vehicles with direct drive e-motor to wheels?
So in a direct drive, depending on the design that we are working with a customer on, the inline unit that we use for rear wheel drive only has an integrated parking pole. For that, we can also utilize e-brake systems for actually direct to the caliper for braking as well. And then if you're using a transfer case designed for an all-wheel drive design, the transfer case that we utilize also has a parking pole integrated into the system as well for parking hold.
Okay, thank you. Next up, for the operational concerns, what are a few of the expected ranges for a 55-ton vehicle with the range extender? Also, can you talk about the dB noise levels for the PTO, high speeds, and high grade operations?
Yeah, I can take that. So in terms of the 55-ton system that we have actually employed the 400 double stack motor on, the range essentially was multiplied by 1.5 times. So the initial internal combustion engine range on a fuel tank, we were able to multiply it by 1.5 times with our 400 double stack range extension system. So that was at least a 50% improvement on the range. Also, in terms of the decibel levels, by regulation for the applications that these systems are going in, we needed to be below 60 decibels. In effect, the electromagnetic design of the motor has been done such that the slot pole combinations eliminate all third, fifth, and seventh harmonics. So from an acoustic noise point of view, this is a highly optimized design. The only acoustic noise that we're able to see is from mechanical fixtures. But apart from that, in terms of electromagnetic acoustic noise, the levels are close to zero. high-speed operations. This system utilized a 8:1 gearing ratio, so it was able to comfortably go at high speeds as well, despite being a 55-ton truck, and high-grade operations as well. So the gradability requirements in this case were, for most cases, for mining applications, the grades were 30% to 40%, which the real-world tests have proven for the system to do very comfortably. So hopefully that answers some questions. But in terms of the torque output from the motor itself, the 400 double stack gives a peak torque output of around 1300 Newton meters. At the higher end on the 430 double stack system, the peak output is around 1800 Newton meters from the motor itself. You couple that with the relevant gearing ratios, and you'll be able to work out what gradability that can do. So hopefully that answers the question.
Okay, thanks so much, Matrishvan. Let's see. What about the mechanical problems for large size axial motors?
So one of the typical mechanical problems that people encounter with axial flux motors is a speed limitation. So when we rate our motors, we make sure that from a simulation perspective and a test perspective, that a scenario for a rotor burst does not occur. So there's fairly detailed finite element analysis simulations which ensure that the rotor integrity is maintained even at high RPM operations. And there's an actual rotor burst test where the banding that I mentioned earlier, the carbon fiber banding that we do around the rotor magnets, ensures that the magnets don't fly off and the rotor does not actually burst. So yeah, both from a simulation and test perspective, there's enough care taken to make sure that high speed operations or high RPM operations do not lead to a mechanical failure. There are other failure modes in terms of bearing lifetime and also insulation lifetime. For insulation, we tend to use the highest class H insulation wires. That gives you high temperature resilience. So even if the electrical losses, the electric heat losses, would lead to temperatures around 180 to 200 degrees Celsius, the wires that we use protect for it and are able to sustain a long lifetime. And from a bearing perspective as well, we use best class bearings. And we do full load simulation on the bearings as well, both from an axial and radial load perspective, as well as a moment of inertia calculation on the bearing lifetime, and prove that we can sustain about 30 to 50,000 hours for a given reference duty cycles. Those are the most common mechanical failure modes, but if there's any other mechanical failure modes that I've not covered, please let me know and I can answer to that as well.
Okay, thanks, Mr. Shen. Next up, is axial flux motor applicable to eVTOL?
Yes, from a form factor perspective, it's really well suited for eVTOL applications. It's a flat pancake profile with enough airflow dynamics around it that will make it suitable for vertical takeoff and lift operations. What you do have to consider for aerospace applications is two primary redesign considerations. The first one is the altitude. So you have to make sure that the creepage and clearances, electrical creepage and clearances within the terminal boxes and electrical connections of the motor are rated to the altitude that you want the eVTOL system to operate at. That typically requires a redesign of the motor. And the other area is aerospace certification. Now, depending on what certification route you're following, you might need to certify something to a DO178 software or DO254 hardware requirement. So again, you need to make sure that right at the outset of your motor or inverter development that you've considered those standards.
Okay. All right, wonderful. Thank you, Matrishvan. We have a few more here. Let's see. With retrofit hybrid solutions, what does a fleet manager need to bring to get you started?
I think the main thing we're looking at when we're talking to fleet owners and fleet managers is kind of a list of what vehicles you're currently using today, route data, which is really, really important. We have a fantastic simulator that allows us to put in how many stops, where those stops are. Then we can look at route topography, traffic history data, and we pull all that together to create a white paper around what kind of efficiency we can increase. And then we also want to look at infrastructure and kind of your terminal design. The other thing that we typically will look at is what direction the customer wants to go around series hybrid, parallel hybrid, or BEV, where series hybrid is kind of the new direction for fleets to go, because they don't require the extensive grid integration and grid and infrastructure capital expenditure, where a series hybrid, one of the really interesting things that we're doing with one of our targeted customers is when they return to the terminal, they're able to put the car in end of route mode, excuse me, and the vehicle will idle and then charge the battery to 100% SOC before the next shift, so that the next shift starts purely on BEV. And this allowed them to see an increase in fuel efficiency and decrease in consumption because the truck is starting out in 100% BEV mode. So it really depends on the fleet, but usage and route information are probably two of the bigger things, and then the platforms that they use in their specific fleet.
All right, thanks, Jason. Matthew is asking for a little more information on eVTOLs. He asks, do you know of any companies that are using this Axial, Flux, and hybrid powertrain solution for eVTOL or helicopters?
Yes, a number of companies. Most of them are in the, let's say, NDA private domain, but something that's in the public domain. If you want to look up a company called Vertical Aerospace, based in UK in Bristol, they're using axial flux-based motor technology and a hybrid powertrain for their eVTOL applications. But yeah, a number of companies, Vertical Aerospace being one of them.
Okay, thanks so much, Matrishvan. What special changes are made for thermal management, cooling challenges?
Yeah, I mean, cooling is a perennial limitation, a thermodynamic limitation in terms of the motor performance. So for your peak ratings, you tend to get away with the electromagnetic performance limitation, but your continuous limits are driven by how much cooling you can effectively manage to sustain a continuous S1 duty cycle. We've done fairly detailed conjugate heat transfer analysis. The purpose of that was to make sure that the cooling channel that we have is optimized, that we use as little of cold plate mass as possible, and we are able to get the highest cooling performance for the lowest pressure drop cost. So after that, we have optimized our designs to basically reduce the cold plate weight. That led to an improvement in our gravimetric power density, and also have a design that is applicable with the lowest pressure drops across multiple stacks of the motor. So yeah, there was a lot of thermofluidic simulation work that has gone into it, but now we have a design that is able to operate with the minimal pressure drop across multiple stacks, as well as provide a sustained, highly capable continuous performance too.
Okay, all right, and how do you cool your system?
It's standard water ethylene glycol mixture. So 50-50 or 60-40 VEG can be easily used for cooling the system. We've tried to steer away from oil-cooled systems for two reasons, mostly because a lot of the applications in which our systems are going don't have a dedicated oil-cooled circuit. But for higher performance applications or for magnet-free applications, we have also analyzed and explored oil-cooled solutions. So it's horses for courses. Depending on your application need and your continuous power need, we can switch between various cooling mediums.
Okay, all right, thank you so much for that, Matrishvan. Next up, is your inverter hardware and software engineered to ISO 26262 functional safety standards?
Yeah, we've got a lot of experience in terms of certifying to ISO 26262. Typically, for a traction slave application, ASIL C is enough. But for other applications where you're using it as a master VCU in addition to a traction slave, you tend to go for ASIL D. So we've done detailed hardware FMEA and software analysis to make sure that we're able to hit ASIL D. This is the seventh generation of our inverter development that we're taking on right now. So all through generation 5 and generation 6 of the inverter development, we have Pro and ASIL C and ASIL D capability, and they're continuing over into the seventh generation of the inverter development as well. One other key addition in terms of compliance on top of ISO 26262 is cybersecurity. So for automotive use cases, it'll be ISO 21434, Cal 2 or Cal 3 compliance that we are targeting for the latest generation of inverter development as well.
Okay, thank you. We have time for a few more now. How much engineering work is usually required to integrate an axial flux motor into an existing vehicle platform?
So what we've done to kind of preempt a lot of the design time that it takes to get it in between, say, a motor and a transmission, or to remove it. We already have pre-existing reference designs that we provide to customers for motor adapters. Some customers will want to move from a basic flywheel to a flywheel torsional coupler or a dual mass flywheel, which we recommend that protects the axial flux motor from torsional forces in the ICE or the diesel motor. That integration is really, really quick. And then from an electrical side, I think right now, the current platform that we're working on, we're at about 80 hours or so of total integration time from start to finish. So anywhere between 80 and 120 hours of integration. What we're trying to do from a company standpoint is for, say, diesel hybrid or ICE hybrid power generation, we want to have those reference designs made for SAE 0 through SAE 4. So we can provide those to a customer. They can adapt those to their specific platform. Whether they want another mounting surface or that sort of thing, you can add that and machine that yourself, or we have a standard model that would be available. We do have transfer case integration designs with third-party designers that are complete. We have an inline drive unit as well that's been designed, that's complete, that are ready to go today. So the mechanical side, we're trying to offer as many options as we can to our customers. And then there's lots of other suppliers that do that same thing. So we have a lot of different options that are available.
Okay, thanks, Jason. How do axial flux motors hold up in harsh environments such as construction sites, mining operations, or heavy-duty truck applications?
You want to take that on, Jason? Or
Yeah, I can. So one of the interesting things is, and for us, we're actually building a prototype and going to be testing a lot of probably in two of the harshest environments you could come up with, to test the durability of the motor. The nice thing about it is, and Matrishvan will probably add a little bit more to this, is the motor's compact design and the distance between our bearings allows the motor to be very, very durable. We also have a very light rotational mass, which helps the motor kind of protect itself in high vibration and high shock load environments. And then also the way that we mount that motor to the back of the block, we use the SAE flange, which is going to provide the most amount of flex protection in the housing and that sort of thing. So they're incredibly durable, and their lighter mass also aids in the longevity of the motor as well. And Matrishvan, you can add some more if you'd like.
yeah, I think in terms of testing the motor, we go through a very extensive design validation program, the DVP of the motor, and all the standards in terms of mechanical durability, be it vibration, shock, thermal cycling, climatic loads, and environmental loads, and substance loads as well, get cycled through. So we tend to refer to the ISO 16750 standard for automotive use cases, and the IEC 60034 from an electrical safety and electrical performance point of view. So the motors go through an extensive design and validation program. On top of that, if there's any application-specific duty cycles that need to be run, we will do that on a per customer basis, as Jason mentioned as well. So yeah, a high level of confidence that the motors have gone through its motions in terms of shaking and baking them, and are fairly durable and robust.
Okay, great. Thank you to you both. And what would you say are the biggest barriers preventing wider adoption of hybrid systems in commercial truck and off-highway vehicles today?
Primarily the development cost. So one of the barriers that OEMs are facing is the development cost of a new platform. Now, if you go with a pre-existing solution that can be easily integrated, like our axial flux motors can be, then that removes the development cost barrier, and homologation barrier as well, because the electrical performance and the mechanical performance of the powertrain system comes pre-certified. The other barrier tends to be cost. So historically, axial flux motors have been seen as a high cost option. What we've done fairly actively at Turntide is work on a cost parity with other radial flux solutions. This will allow for hybrid systems in which the axial flux motor gets integrated to be very easily integratable into OEM platforms on a cost parity basis. So those are the two key areas where I see we are working to prevent and accelerate tackling those barriers down. Yeah. Jason, anything else you want to add to that?
I think from the commercial vehicle side, I think the biggest barrier that we've seen so far with a lot of customers is whether it's been adopted by an OEM or whether they're going to convert a fleet. So if you have a larger fleet that's maybe privately owned, one of the advantages that we bring is that we can retrofit current platforms and allow that platform to have a second life, where having a brand new truck and having it, trying to find a way to get a brand new vehicle that has a hybrid drivetrain in it. A lot of the larger OEMs were just not there yet. So I think that's probably one of the bigger ones. And that's where, private fleet owners and that sort of thing, the series hybrid retrofit industry is gaining so much momentum.
All right. Well, let's take one more before we go. You mentioned fuel savings of 15 to 20% in some applications. What type of vehicle duty cycle was that based on, and what results are customers seeing in real world use?
Go ahead, Matrishvan, go ahead.
No, I was going to say that the 15 to 20% figure is a relatively conservative figure that we've been using. Duty cycles tend to range from your standard WLTP to a mining truck application duty cycle, which is specific to the customer. In terms of real world efficiencies, as I mentioned, the example of a range extension by over almost 50%, or by just adding the AF400D onto a mining truck application, that's been seen in real life. So the 15 to 20% figure is a conservative floor that we have. In terms of the ceiling, depending on how well you do the power blending between your ICE engine and your electric powertrain, determines how much efficiency and range you can eke out of it. And I'm sure Jason's got some other real world examples that he can speak to as well.
Yeah, we're one of the tests that we're going to be running over the next, let's say, next 90 days to 120 days in California is last mile delivery. So a light duty last mile delivery route with, it's a 60 kilometer route, or about a 50-mile route. It's got 62, 63 stops in it. We're going to be running a range extended platform and then a diesel platform together in California environment. So high temperature, lots of hills, lots of grade, lots of stop, lots of traffic. So we're going to be testing that in California specifically to validate, a 25 to 30% fuel efficiency increase. So we'll have that data, available pretty soon as well. So that's a real world test, in traffic, live test, not on a, on a dyno, on a route that's, doesn't have traffic. It's going to be real world testing. So we're really excited about that testing.
All right, great. Thanks. Everyone be on the lookout for the results. All right. Unfortunately, that's all the time we have for questions today, but I would like to thank Jason Glass and Matrishvan Raval, as well as our audience, for joining us. And thanks to all of you who submitted questions. We'll supply the speakers with any questions that came in for follow-up later. As a reminder, you may download a PDF of today's slides as well as other resources from the resources box. Please use the on-screen survey to tell us what you thought of today's program, which will be available on demand for the next year. You'll receive a link to the recording when it's ready. Once again, we thank you all for watching.
Thank you, everyone.